All right, let's take a look at a few more situations that could arise with related rates. This first one here looks pretty similar to questions that we've already talked about. We're just talking about pumping air into a spherical balloon. All right, but let's take a look at this one and see what differences may arise. So it says air is being pumped into a spherical balloon at a rate of 22 cubic centimeters per second. What is the rate of change of the radius at the instant the volume equals 27 cubic centimeters? So this first piece of information, right, is a rate. Okay? It's the rate of change of the volume. So we're talking about cubic centimeters. So I'll go ahead and jot that down here. So dV dt is 22 cubic centimeters per second. Then we want to find the rate of change of the radius. So dr dt is what I want to find. Now this last piece of information says at the instant the volume equals 27. Right? So I want to find dr dt when v equals 27. So we'll see how that comes into play later. All right, but first, let's just think about taking our derivative here, relating the rate of change of the volume to the rate of change of the radius. So when we do that, we'll have dV dt equals, when I bring this 3 down, 3 times 4/3 is just 4. Subtract 1 from the exponent, then times dr dt. So I know dV dt, I want to find dr dt, but I don't know the radius. Right? I need to find the radius still. Well, they've given us this piece of information that will allow us to find the radius. I want to find the radius when the volume is equal to 27. So what I want to do is set 27 equal to the volume. Right? So I'm going to come off to the side here and say 27 equals 4/3 pi r cubed. Right? This is my volume formula, and I'm saying the volume equals 27. I want to solve for r here to plug into this formula. So to do that, I will multiply both sides by 3/4 times 3/4. So over here, we get 81 over 4 equals pi r cubed. Now I'll divide by pi. So when I do that, I'll have 81 over 4 pi equals r cubed. Now just take the cubed root of both sides, and we end up with this big ugly number. Right? The cubed root of 81 over 4 pi is equal to r. Right? I mean, that's fair game to get a number like that. Right? So now I have this piece of information that I can plug in over here. So I know dV dt is 22. Right? So 22 equals 4 pi, and now I'm going to plug this whole thing in for r. So times the cubed root of 81 over 4 pi. That cubed root should extend all the way down there, and that's squared. Right? We want that radius squared times dr dt. So here I'm just solving for dr dt. Well, to do that, I'm just going to divide both sides by this whole thing here. 4 times pi times the cubed root of 81 over 4 pi squared. So I will get 22 over 4 pi times the cubed root of 81 over 4 pi squared. And my units, since we're talking about the rate of change of the radius, would just be centimeters per second. So the different thing on this one was we had to go back and find a piece of information that we needed. Okay, it's kind of similar to the Pythagorean theorem problems, where we had to use Pythagorean theorem to find a piece that we were not given. Okay, and in this case, we had to go back and use this piece of information, okay, that the volume was 27 at this instance to find R, to find this missing piece of information in my derivative. Okay, so there will be problems like that where we have to use what's in the problem to find some other missing piece of information. Okay. The next type of problem that I want to take a look at is a cone problem. Okay, and we're going to do a couple examples of this one because this one has seemed to show up on AP tests frequently. So let's just read through it and see what we have. In this one, it says a conical paper cup is 10 centimeters tall with a radius of 10. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? So let's kind of sketch out what's going on here. So we've got a cup, right? A conical paper cup. We know that the radius is 10. Actually, let me, oops, didn't want to undo all of that. Just wanted to go for a different color here. So we know the radius is 10, and we also know that the height of this paper cup is 10. All right, and we're saying we've got water inside of this cup. All right, this instance that we care about, right, that we're going to eventually work with, is when the water level is 8, right? So we're saying we filled up the paper cup all the way to here, where the water level is 8. Well, we know that we're working with volume of a cone, right? So volume of a cone is 1/3 pi r squared h. So let's kind of collect some of this information that we have. All right. Well, it tells me that water is being poured into the cup so that the water level rises at a rate of 2 centimeters per second. Okay, well, that's the rate of change of the height, right, where the water level is rising. So my dH dt, we know, is 2 centimeters per second. Then we are given that the instance that we care about is when the height is h, right? And we want to find the rate that water is being poured into the cup. So that's going to be the rate of change of the volume. Right? I want to find dV dt at the instance when h equals 8. We're not given any information about the radius or the rate of change of the radius. This is a common problem they put on the AP test because we are going to have to manipulate our original formula a little bit. What we are going to have to work with is similar triangles here. Okay, so what we know for sure is that this cup, and this cup isn't going to change size, right? This cup has a radius of 10 and a height of 10. Okay, well, this instance that I care about, we're just going to say is R and H. We want to think about these similar right triangles here. So what I can do here, I can say that R over H is equal to 10 over 10. Right? R over H is equal to 10 over 10. Now, I'm only given information about the height, about dH dt, and about h. So what I want to do is only write my volume formula in terms of h. And what that means is I want to solve this proportion for r and plug something in terms of h in for r here so that my volume formula will only be in terms of h. So what that looks like, right, if I just solve for r, all I'm going to do is multiply both sides by h. So we get r equals 10 over 10, which is just 1 h. Right? So in this case, I can just replace r with h. So in my volume formula, I can say this is just 1/3 times pi times h squared times h. Now this obviously then would just be h cubed. So I can say my volume is 1/3 pi h cubed. Now, this makes finding this derivative a whole lot easier, right? Now, the reason we're able to do this is because we know that neither the height or the radius of this paper cup are changing, right? This ratio, okay, as we pour water into this cup, this ratio of this rate to the height isn't going to change, right? So now we can take our derivative. Right? My derivative here would be dv dt equals, now when I bring this 3 down, 3 times 1/3 is just 1, so we end up with pi h squared dh dt. So now we can plug in what we know, right? I know that at this instance, h is equal to 8 and dh dt is equal to 2. I'm solving for dv dt. So we get dv dt equals pi times 8 squared times 2. So what is that? 64 times 2 is 128, so I'll just leave it as 128 pi. And since we're talking about volume, this would be cubic centimeters per second. Okay, so this similar triangle idea, right, is a pretty popular idea on the AP test, right, where you need to manipulate this volume formula, right? So we're going to take a look at a couple more examples here. Now, on this third example, okay, you might want to pause the video, see if you can figure this out on your own before you go on, right? All right, so let's take a look at what we have here. So it says James is filling an ice cream cone. So kind of similar to the last one, right? We were just filling up a conical paper cup with water. Here we're filling up a conical ice cream cone. It says the cone is 12 centimeters tall and has a radius of 4. So "12 centimeters tall." So I can just do that. And the radius is 4. Right? And again, we know volume of a cone is 1/3 pi r squared h. Let's take a look at what else we know. So it says if the ice cream fills the cone evenly at a rate of 1.5 cubic centimeters per second, what is the rate of change of the height when the height is 5? So here we're given the rate of change of the volume, right? I know that dv dt is 1.5 cubic centimeters per second. I want to find the rate of change of the height. So I want to find dh dt when h equals 5. So notice again, we're not given any information about the radius or the rate of change of the radius. So we need to use this same idea, similar triangles, okay? So what we can say, I'll sketch this idea out again here. And I know this is 4 and this is 12, and we're taking some smaller piece, right? We're saying we're just looking at whenever the ice cream is filled up to when h is 5. So we're saying, well, this is r, this is h. I can set up a proportion here. I can say R over H is equal to 4 over 12. Now, again, I just want my equation to be in terms of H. So I want to solve for R and plug that in for H. So if I do that, if I multiply my H over to this side, I'll end up with R equals, now 4 over 12 reduces to 1/3, right? So I just get R equals 1/3 H. Now this I can plug in for R in my volume formula. So I will say volume is 1/3 pi times 1/3 H squared times H. So now if I simplify this, volume is 1/3 pi, 1/3 squared is 1/9, right, times H squared times H. So now I can put all this together and get 1/3 times 1/9 is 1/27 times pi times H cubed. So now again, I can take this derivative very easily. Right? I only have one variable on this side. I don't have to worry about product rule or anything like that. So let's take my derivative, plug in what we know, and see what we can do with that. So dv dt, if I bring this 3 down, 3 times 1/27, 3/27 would be the same as 1/9. 1/9 pi h squared times dh dt. So what I want to find is dh dt. Right? I know dv dt is 1.5 equals 1/9 pi. Actually, since we're working with a fraction here, I'm going to go ahead and change this 1.5 to a fraction. I don't really like having decimals and fractions in the same equation. So 1.5 is the same as 3/2. Right? So over here then, h we said was 5 squared times dh dt. So let's see, I'll continue this up here then. So 3/2 equals, so we'll have 25 ninths, right? So 25 ninths times pi times dh dt. Well, to get this 25 ninths to the other side, I'll multiply by the reciprocal, so times 9 over 25 times 9 over 25. And over here we get 27 over 50 equals pi times dh dt. Then all I have to do is divide by pi, and we get 27 over 50 pi. Let's see, so my units, since we're just talking about height, would be centimeters per second equals the rate of change of the height. Okay, so again, we had to use this similar triangle idea to write my volume formula just in terms of a single variable, right? Because we weren't given any information about the radius or the rate of change of the radius. All right, let's do one last example here. And again, maybe pause the video and see if you can come up with anything on your own here. All right, let's take a look. So a pile of sand in the shape of a cone, whose radius is twice its height, is growing at a rate of 5 cubic centimeters per second. How fast is its height increasing when the radius is 20 meters? All right, so let's take a look at what we know here. So let's see. We know that the radius is twice its height. Right? So actually, oops, this one will be the other way. Right? This will be a cone shaped like this that's growing. Right? So Let's see what we have. Radius is twice the height. So just jot that down. I know radius is going to be 2 times the height. The pile itself is growing at a rate, so that will be dV dt is growing at a rate of 5 cubic meters per second. So meters cubed per second. How fast is the height increasing? So what I want to find is dH dt when the radius is 20 meters. All right. So when r equals 20. All right. So again, we know volume of a cone is 1/3 pi r squared h. Notice, yet again, we are not given any information about the rate of change of the radius. Even though we are given information about r itself, we're still not given any information about the rate of change of the radius. All right? Now, that means we still only want our original function to be in terms of h. And we're going to have to use this idea here. Okay? We don't even have to set up a similar triangle. We're just given this key piece of information. Right? The radius is twice the height. So what I want to do is plug this in to my volume formula. So volume is 1/3 times pi times 2h squared times h. So volume is 1/3 pi. So remember, we have to square both of these pieces. So this would be 4h squared times h. And if I simplify that, we get 4/3 pi h cubed. All right, so let's take our derivative. So dV dt equals, if I bring my 3 down, that would just be 4 pi h squared dH dt. All right, so I know my dV dt. That's just 5 equals 4 times pi. Whoa, I don't know what h is. I know what r is, but I'm not given h. Well, all I need to do to find h is use this key piece of information here. Right? I know that r is equal to 2 times h. So I can say that 20 is equal to 2 times h. Just divide both sides by 2, and we get that at this instance that we care about, the height is equal to 10. So go and plug that 10 in, and we want to solve for dH dt. So we get 5 equals, we get 100 here, times 4 is 400 pi dH dt. So then all I need to do is divide both sides by 400 pi. We will get 5 over 400 pi. We're talking about the rate of change of the height. So this will be meters per second equals dH dt. All right. So in these problems that we've looked at today, okay, we had to first, in number 1, okay, use this piece of information to go back and find another missing piece of information. We had to actually do that same thing here in number 4. Okay, we had to use this given piece of information to go back and find another missing piece of information that we needed. Okay. The other big idea from this is this similar triangles idea. Okay, this cone idea shows up a lot on the AP test. Right? Seems like one of these shows up every other year. So this is something that we need to be comfortable with. Right? Writing this volume formula just in terms of one variable. Right? All the examples we looked at were solving for r and then plugging that in to get our equation just in terms of h. That's the majority of what showed up on the AP test, okay? But it could be the other way around, right? We could have to write our entire volume formula in terms of R if we're given information about R and dr dt instead, okay? So we're going to have just a set of practice problems for you to work on in class on Wednesday, and then that will carry over then into Thanksgiving break, okay, that you'll be able to finish those up.